He's going to talk about how to use machine learning to speed up program synthesis.
Thank you. This is a joint work with Ki-hong, Rajiv, and Meyer. The goal of program synthesis is to automatically generate a target program given a high-level specification. Such a specification can be given using a standard formulation called syntax-guided program synthesis, shortly SyGus. The formulation comprises a syntactic constraint in the form of a context-free grammar that constrains the space of all possible programs, and a semantic constraint in the form of a logical formula, which defines a correctness condition that a target program must satisfy. This standardization established various applications from widely applicable domains. And there are three most popular general-purpose synthesis strategies: enumerative approaches enumerate candidate programs in order of increasing size with a search space pruning technique. Symbolic approaches cast synthesis problems as constraint-solving problems, and stochastic approaches keep mutating an initial candidate program, which is randomly sampled from a search space. Despite significant strides in these approaches, however, a key limitation is that they do not guide the search towards likely programs. They assume all possible programs in the search space equally likely. As a result, they explore many undesirable candidates in practice, which will be shown with an illustrative example later. Our goal is to avoid such many unlikely programs. Let me explain what I mean by likely programs. It is well known that programs often contain repetitive and predictable patterns. For example, consider an IDE into which a programmer has typed into this partial for-loop statement. It would be quite reasonable for the IDE to suggest a conversion I++ to the programmer. Another possible option, I-, is highly unlikely because it will make this for loop infinite. By exploiting such statistical regularities in programs, statistical program models define a probability distribution over programs. And thanks to the large and growing body of open source programs, there have been many various statistical program models proposed and proven successful in a variety of applications, such as code compression, deobfuscation, program repair, among many others. Inspired by this success, we'd like to answer these quick questions. Can you leverage statistical program models to accelerate program synthesis? Our answer is yes. And to solve this problem, we have modularly addressed two orthogonal but complementary challenges. First, how to guide the search given a statistical model. Second, how to learn a good statistical model. Let me summarize our contributions as follows. To address the first challenge, we propose a general approach to accelerate SyGus-based program synthesis by using a probabilistic model to guide the search towards likely programs. We target the widely used SyGus formulation, and we support a wide range of various program models. To address the second challenge, we employ a learning method inspired by transfer learning to mitigate overfitting. We have implemented our method on top of a tool called Euphony and evaluated it on widely applicable domains. Both the tool and artifact are available for download. In the rest of the talk, I will describe overall architecture of our system and illustrate example and evaluation result. Our system comprises two parts, the searcher and the learner. The searcher takes a high-level specification and a probabilistic model and generates a solution which is correct with respect to the specification. During the search, the given probabilistic model is used to guide the search. A learner trains a probabilistic model from a labeled corpus of existing programs. Let me describe each of them. The searcher internally uses the SyGus procedure which comprise two components, the generator and the verifier. The generator keeps producing program candidates until it finds a program that the verifier certifies to be correct. The overall performance of this SyGus procedure is heavily dependent on the generator. So our method allows the generator to explore candidate programs in order of likelihood determined by the given probabilistic model. To guide the search well, we certainly need a good model. However, blindly using existing statistical program models often leads to an overfitting. Our solution is to generalize to unseen programs better using a feature map designed by a domain expert. In this talk, I will not cover this part. Please refer to the paper. Now I will describe how our guided search works with an illustrative example. Let's suppose we want to synthesize a function f that takes a string denoted x as input and outputs a string with each hyphen in x replaced by a dot. The syntactic specification is given in this form of context-free grammar. We consider programs that can perform string concatenation and replacement operations. The semantic specification follows the programming by example paradigm and comprises 3 input-output example pairs. In this setting, a desired solution will look like this. We next illustrate how a typical enumerative synthesizer finds this solution using the SyGus procedure. The generator explored candidates in order of size. It first proposed arbitrarily a small program to the verifier. Let's say the expression, a single dot. The verifier checks the correctness of the proposed program with respect to the specification. And if it is not correct, it yields a counterexample, this, because the output of the expression on this counterexample input does not match the desired output, which is dot dot. In the next iteration, the generator searches for a program that is correct with respect to the counterexample, and it enumerates candidate programs in order of increasing size. So it eventually finds this program that concatenates 2 dots, which is correct with respect to the counterexample, but incorrect in terms of the specification. So the verifier generates another counterexample. You may wonder, it just enumerates candidates like a DOM. It is not true. It employs a powerful pruning optimization technique to prune the search space. For example, a program that concatenates hyphen and dot is not explored because it is equivalent to this program, X, under the counterexample. In this manner, it can prune the search space significantly. In the third iteration, the generator eventually finds the desired program, which the verifier certifies to be correct. In general, the number of enumerated programs are exponentially many in program size, despite the powerful optimization technique. Since it assumes all possible programs are equally likely, there are many unlikely programs explored. For example, a program that concatenates 2 dots is not likely at all because it does not involve the input. We propose a weighted enumerative algorithm to avoid such unlikely programs. Our algorithm is essentially the same as the existing enumerative approach, except that it enumerates candidate programs in order of likelihood. The generator first proposed this program instead of enumerating all the smallest expressions, because it is the program of the highest probability among all possible programs. The verifier yields this counterexample for a similar reason. In the next iteration, it quickly finds the desired solution because it avoids many unlikely candidates. And also, we preserve the pruning optimization technique used in the existing approach. Next, I will detail how we prioritize the enumeration. We assume a uniform interface to statistical program models. Any models that fit into our interface can be used for our guided search. The model takes a sequence of terminal and non-terminal symbols, so-called sentential form, and provides a probability for each production rule. For example, this model says in this sentential form, the non-terminal S should be expanded to a dot with a probability of 0.72. The interface is quite general enough to embrace Ngram, PCFG, and so on, many existing models. Assuming such a model is given, we first construct a directed weighted graph. In this graph, each node represents sentential forms that can be derived from the start non-terminal symbol S. And each edge is associated with the production rule. And this edge means sentential form S1 expands to S2 by applying a production rule R to the leftmost non-terminal symbol. And each edge is associated with the real-valued weight, which is the negative log probability of the corresponding production rule. In this setting, the sum of the weights on a path from S to a node representing a program is the negative log probability of that program. Now we solve the single source shortest path problem. We have a single start node S and multiple goal nodes which represent all possible programs in a search space. So we have infinitely many goal nodes potentially. Then enumerating programs in order of decreasing probability corresponds to enumerating goal nodes in order of the shortest distance from S. And we use a star search algorithm for pathfinding. And one noteworthy thing is we propose a heuristic function, which is used in a star search to guide the search. And the heuristic function was designed to work with any model. We have evaluated our tool euphony on around 1,200 synthesis problems collected from the last year's SyGus competition and online forums. We compare our tool to EUSolver, which is the winner of the last year's SyGus competition, and FlashFill, which is the best domain-specific synthesizer for string processing in spreadsheet. We chose synthesis tasks from 3 different application domains. The string domain comprises 205 problems faced by spreadsheet users, and the bit vector domain comprises 750 problems for finding bit manipulating programs from input-output examples. And the circuit domain comprises 212 problems, and each problem is given a cryptographic circuit to synthesize another circuit that is functionally equivalent to the original circuit and secure against side channel attacks. We first compare euphony with EUSolver. We learn a statistical model by training on easily obtainable solutions that EUSolver can solve within 10 minutes and generalize it to solve harder problems. Among 405 testing instances, euphony could solve 236, whereas EUSolver only could solve 87. And these figures shows the cumulative running times of both solvers, and each figure shows the number of benchmarks solved within a given timeout limit. For instance, in the bit vector domain, EUSolver could solve only 50 benchmarks within 1500 minutes, whereas euphony could solve around 180 benchmarks. We next studied the result for the string domain. Out of 82 testing instances, euphony could solve 27 problems. The chart in the right shows the synthesis times for both solvers. And euphony could solve 78% of the solved 27 instances within a single minute. And it solved 8 problems on which EU solver timed out. And it outperformed EU solver on all the instances. Next, we compare euphony with flash fill. Among 113 problems that can be handled by flash fill domain-specific language, again, we train a model from easily obtainable solution by running flash fill in 30 seconds and apply it to solve harder problems. In terms of the number of problems solved, flash fill is better because euphony timed out on 2 instances. But in terms of synthesis time, however, euphony significantly outperforms flash fill. In the paper, you can find general heuristic function for A-star search and how to preserve orthogonal search optimization, feature maps for the 3 application domains, and effectiveness of different statistical program models. Thank you for listening.
Any question?
Hi, thank you for the talk. So I had some questions about since you're guiding the search, right? So do you actually change your probability distribution using the counterexamples? Do you actually add from the SyGus search?
Change.
Do you update your probability distribution doing the search, or is it static?
No. The probabilities remain to be the same.
Is it always the same, right?
Always the same.
Do you thought about how can you use maybe the counterexample to change the probability during search?
No, it's not relevant to counterexamples at all.
No, but
yeah.
I'm just saying, maybe let's say you're guiding the search towards a space that is not actually the correct one. When it works, it's great, right? But let's say it's not working well. Maybe the information that you get from the SyGus loop could actually help you now guide the search somewhere else. Because since you actually have a static probability distribution, could be that you can get stuck in, let's say, a local minima or a search space that is actually incorrect for that example. So maybe that could be something that could be interesting to explore.
I see. Yeah.
Just some ideas.
Yeah, I think it's quite interesting idea. Yeah.
Right, thank you.
Yeah.
So in your experiment, have you tried doing cross-validation? I'm wondering how stable the model is.
Yeah, that's a good point. Because we don't have enough instances for cross-validation, because we only have 1,200 instances, and actually it's not that many for learning a rich statistical model. So we didn't do cross-validation experiment, but we are planning to do that later after we get more benchmarks.
Thank you.
Yeah.
Let's thank our speaker again.